Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in Silicon Valley, and it's a great pleasure for me to welcome everyone in the auditorium and everyone listening or viewing us on the web to this lecture in the 11th annual Silicon Valley Astronomy Lecture Series. This is a series sponsored by the Foothill College Astronomy Program, by the NASA Ames Research Center, one of the premier NASA centers around the country, by the Venerable Astronomical Society of the Pacific, which is devoted to sharing astronomy with the public since 1889, and by, appropriately tonight, the SETI Institute, the Search for Extraterrestrial Intelligence Institute, which is devoted to the science and education of the search for life in the universe. This is a series of 6 programs every year where noted astronomers share with us the exciting results of what's happening in our quest to understand the universe. Tonight's speaker is Dr. Seth Shostak, one of my personal favorite speakers in the world of astronomy, who's going to talk about the search for intelligent life among the stars, new strategies. Dr. Shostak is senior astronomer at the SETI Institute and a spokesman not just for the Institute itself, but for astronomy in general. You often hear him on local and national radio and television programs. He also hosts his own syndicated radio show called Are We Alone?, which is broadcast locally here in the Bay Area on KALW and KLIV, and can be heard on the web. If you go to the SETI Institute website, you can find that program. And every week he has exciting guests talking about interesting developments in science and science's relationship with other fields. Dr. Shostak has written hundreds of articles and web pages on the quest for life elsewhere and other topics in astronomy and astrobiology. He has a degree in physics from Princeton University and a doctorate in astronomy from Caltech. For the last 6 years, he's been a distinguished speaker for the American Institute of Aeronautics and Astronautics. He's written and edited a number of books on the search for life elsewhere, and his most recent book is designed for the public at large. It's called Confessions of an Alien Hunter, a scientist's search for extraterrestrial intelligence. It was published by National Geographic Books, and I highly commend it to everyone who's listening to this lecture. So we've asked him to talk about one of his favorite subjects, the search for cosmic company. It's a distinct pleasure and a privilege to introduce Dr. Seth Shostak.
Thank you very much, Andy, for such a nice introduction. I'm afraid that the packaging will be better than the meat, but it's very nice. And I also, by the way, always warn audiences not to applaud beforehand because you will always have regret later. It's nice to be back at Foothill College. Actually, when I first came to this part of California more than 20 years ago now, I had a lot of free time, which is not the case now, but I had quite a bit of free time in the evenings, and I came up here and took some courses in creative writing, actually. It was somewhat by accident. I just wandered into the wrong room by mistake. And I have the fondest memories. I think that Foothill College, to the extent that I can write, taught me how to write. So it's very nice to be back here and to be back part of the lecture series. It's been a while since I've given a talk here. My last talk was what happens if we find ET, and in that I described a little bit about how SETI, and in particular the SETI Institute, which, by the way, I don't know if Andy mentioned, is in Mountain View, so a local institution here, how we're doing the experiment. Tonight, I'm going to simply try and provoke you. This is not entirely malevolence, but it's just to suggest other ways of doing SETI that you might think about. And if the hit rate on these ideas is as much as 5 or 10%, that'll be pretty good as far as I'm concerned. So first off, here's just a picture of the universe, or part of it. You see a whole bunch of stars. There's some, hot gas and so forth there, some cold gas you can't see. In the background, some galaxies. The number of stars in our galaxy is on the order of a couple of 100 billion. I think most of you know that number. the question that has been asked now for a very long time and that we're finally getting an answer to is, well, how many of them have planets? Now, those of you who follow this thing know that we've discovered more than 400 planets around other stars. That per se is not so interesting. What's really interesting is what fraction of stars have planets. And if you talk to Jeff Marcy, who's spoken in this series, or other people who look for extrasolar planets and say, well, Jeff, if you had perfect instruments, what fraction of stars do you think would show planets? And he says, well, maybe half, maybe 3/4. Okay? Now, for an astronomer, half is the same as all. Okay? You don't worry about factors of 2. In astronomy, pi is 1 or something like that. So what that means is that there are on the order of 1 trillion planets in our Milky Way. And if none of those seem suitable enough for you, if you're particularly picky about your planet, you can always go to another galaxy and find another 1 trillion planets. But this is a big number. I just want to emphasize this. People say, why do you think there's life out there? There was a reporter at the Institute recently who asked me, do you really think they're out there? Which I found a very bizarre question to ask of someone who's working at the SETI Institute. I mean, you know, why would you do it? But I said, yes. And he said, well, why? And I said, well, it really comes down to this. It just comes down to this number, because if only 1 in a million of those planets meets the requirements for your gusto-grabbing, free-living lifestyle, that's still 1 million worlds just in our galaxy. So, you know, the numbers look good because they're large. There's something else. There are other indications that might suggest to you that maybe what's happened on this planet is not really a miracle, and that is the fact that life got started here very early. This is a photo I made down in the northwest corner of Australia in the Pilbara Hills. You see these sort of round things. This laser pointer isn't really a laser pointer. It just I'll telepathically tell you where to look. And there's a business card there for size or something like a business card. You see those round things that look like frozen cantaloupes. Those are fossilized stromatolites. Okay, those are just the colonies of bacteria. And we know how old this rock is from radioactive dating. We know that fairly accurately. It's about 3.4 billion years old. What this is saying is that 3.4 billion years ago, right, there was plenty of life on Earth. So since the Earth is only 4.5 billion years old, what this is saying is that life got started very quickly on Earth. And that suggests, doesn't prove, it's only an example of one, but it does suggest that life wasn't a very difficult experiment. Certainly not an improbable experiment, because it got started very quickly. Okay, so how are we looking for not just life, but the kind of life that could hold up its side of the conversation, namely intelligent life? Well, I think many of you heard Jill Charters speak here recently talking about the Allen Telescope Array, which is a joint project of the SETI Institute and the University of California at Berkeley, to build our own telescope to do this sort of search. And for the Berkeley people, also to do some top-notch radio astronomy. By the way, there's a dime in this photo for scale, but if you don't see it, you can see me going around flashing the antennas. This thing is located about 300 miles from where you're sitting, up in the Cascade Mountains of northeastern California. And it's located there, by the way, not because of the cuisine, but because it's surrounded by mountains and therefore shielded from all the interference from the Bay Area. In any case, it's named after Paul Allen, who's given the money to get this thing underway. And it's, as I say, an instrument that's really designed from the get-go to be very good for SETI research. This is a big step forward, by the way, because people will often say, SETI is celebrating its 50th year this year, in fact, in April. You haven't found anything? Doesn't that embarrass you? Or, don't you get discouraged or something like that? Keep in mind, we've had to do these experiments intermittently using other people's antennas. So, it's like trying to find the cure for cancer, but always having to borrow the microscope. It's very slow going. This will have an in-house telescope. We can use it 24/7. That's a factor of 10 improvement in speed right there. Covers a very much wider range of frequencies. These are all technical things. There will be a few technical things in this talk, not too many. I'm told that every time you show a graph, this was a lesson I learned in grad school, every time you show a plot, you lose 10% of the audience. So I have 12 plots in this talk. Put them all at the beginning so that you don't have to suffer long. And it can also, this is a really important point, and this has to do with the nature of antenna arrays. It can look at more than one star at a time, so you're not just looking at one star and then looking at another star and looking at another star. When I say looking at a star, of course, I mean we assume that they have planets around them. This is an aerial shot I made about a year ago. There are currently 42 antennas in this array, but the design goal is to make 350 of them. But it's not the only way we do SETI. We also do optical SETI, so-called optical SETI. And this is a photo up at the Lick Observatory. This is a telescope that's about 1 meter in diameter. So it's, you know, a small telescope, an old telescope, but perfectly adequate for aiming at nearby stars, using some electronics in this white box behind. That, by the way, was put together by Shelley Wright here, who was a student at the time, an undergraduate student at UC Santa Cruz, and look for very brief flashes of light. Right? If you get a brief flash of light in a nanosecond, in a billionth of a second, and maybe you count, you know, 100 photons or 1,000 photons, that's got to be something special, because the stars don't do that. Right? A star 100 light years away, like the sun, would produce less than 1 photon in a nanosecond for a 1 meter telescope. So this is another way to look for life in space. They may be flashing us with their lasers. So we have these dual approaches. Now, this whole field was begun, as I mentioned, 50 years ago by Frank Drake. Here's Frank. He always put on a tie and a jacket when he's standing out in the cold there in West Virginia. This is the 85-foot antenna that he used in the spring of 1960, pointing it at 2 nearby stars, hoping to eavesdrop on signals coming from those stars. This was Project Ozma. And he started what is known as today's targeted search strategy, because he didn't point the antenna at random. He picked 2 nearby stars. They were about 11 or 12 light years away. They were stars like the sun, and he looked at first one and then the other. He actually scored on the second one. He got a signal, but it turned out to be the U.S. Air Force, so that didn't count as alien intelligence. There you go. Okay, now, I want to emphasize, this was the strategy that was chosen then, and this is the strategy we still use a lot today. The SETI Institute is very keen on targeted searches, and the Allen Telescope Array is planned to also look at individual stars, okay? And the idea is that you look at the nearest ones first and you work your way out. But I'm going to suggest tonight some alternatives to that. Now, this plot, which was made up for a magazine article, just gives you some idea of how much search space we've looked at, right? I mean, you're looking for ET, you haven't found it. Well, this tells you why. These are all the, you know, just a couple of the parameters of the signal, right? They've just been plotted as 3 axes here. And you can see various experiments. Actually, this Allen Telescope Array is, you know, for the future. We haven't actually filled that in yet. So you can see that very little of the search space has actually been examined, right? And so when people come up and they say, you know, you haven't found anything, you guys ought to give it up. And I get emails like that every day. I respond to them that this is completely analogous to going to Africa in search of megafauna, right? Landing your ship on the shore and examining one city block of Africa and then saying, well, that's it, no hippos, no elephants here. You know, I think I'll go home. There's no megafauna. There are no megafauna in Africa. And that would be early days. That would be premature. The same with SETI. Okay. Now, the Allen Telescope Array has a design goal of not 42 antennas, which is what it has now, but 350. Okay. Now, building the rest is pretty straightforward. We know how to do that now. What's missing here is the check. So if one of you want to buy an antenna, you can buy an individual antenna. I recommend you buy the whole array. It's per antenna less expensive for you. And so that's the deal here. This is the possible result of that. Okay, what's plotted here? This is one of those 12 plots. What's plotted here, I just did a little bit of geometry here and then an extrapolation of what this instrument will do in the future, because we know what the technology will do. You're all well aware of Moore's Law. You live in the Silicon Valley. You know that the price of computers drops by a factor of 2 at any given performance level every 18 months. So the same is true for SETI. SETI is mostly digital electronics. It gets faster all the time, doubling in speed on average ever since Frank Drake's original experiment every 18 months. So what I got plotted here is how far out into space, how far out have we examined all the interesting star systems? Okay, so, you know, here 100 light years out, and then, you know, a few years later we're at 200 light years and so forth. What's really interesting here are these numbers. These are what are called estimates, which is a euphemism for guesses as to how many societies are out there broadcasting a signal we could pick up. Carl Sagan figured there might be 1 million. If he's right, then we should trip across ET before 2015. Isaac Asimov figured 670,000, and it takes till 2022 or something. Frank Drake himself typically says 10,000. Okay, now, I've asked Frank many times. I don't know if Frank's in the audience. He may be here. You can ask him why he came out, or how he came up with this number, and that's some sort of secret sauce. But in any case, it's the most conservative number, and even if you take the most conservative number, then it's still the case that this experiment's going to pay off in 24 years. Okay. All right, now you might say, yeah, but these are all guesses. They're all guesses, and they are. They are guesses. But on the other hand, these are guesses by people like Carl Sagan, Frank Drake, and so forth. These are the people that motivated this whole search. So if you feel sufficiently impressed with the arguments that have been made for doing this, then the result of that is that you should expect success fairly quickly. Right? This is not like building Salisbury Cathedral in England, which took, I don't know how many centuries it took to build that pile of stones there, okay, where you say, well, my great-grandkids will do it. Either it's going to work within a generation, or there's something fundamentally wrong with the premises. Now, I think we might even be able to speed things up, but in order to do that, you have to know this number here. Typical sensitivity for SETI, these are the best numbers, but these are the sorts of things you can get down at Arecibo, and maybe eventually with the Allen Telescope Array when you get it built out, is 10 to the minus 25 watts per meter squared. Okay, that's the weakest sort of signal you could find coming in on a 1 hertz channel and so forth. Now, what is that? Well, I mean, it's just a number, but let me give you another example. If you take one of those Allen Telescope Array antennas and you aim it at the sky and you're collecting a signal that's at that level, and you've been doing that ever since the dinosaurs were snuffed, in other words, for 65 million years, after 65 million years of collecting that with one of our antennas, the total amount of energy we'll have collected is the amount of one ant raising one leg once. Okay? So it's not a lot. I mean, that would suggest to you, that should impress you in something. Very little of this talk will impress you, but that should impress you because that shows you how good radio technology is. You can find very, very weak signals, okay? And it sounds like we should be able to find really pipsqueak transmitters out there. But, of course, space is vast, all right? And the consequence of that is that the signals, of course, are attenuated by distance. So here's a computation. This is another number you can, if you don't like this number, you can try this number here on the bottom at your next cocktail party. Let's assume that the aliens were aiming an antenna our way, trying to get in touch because they want to sell used cars or whatever. They're 1,000 light years away. That's pretty far. That's farther than we generally look, but let's say 1,000 light years away, they've got an antenna as big as the one down in Puerto Rico at Arecibo, which is 1,000 feet across, right? Hold 4 billion scoops of Baskin-Robbins. All right, they've got that aimed at us, and we're looking at them with a similarly sized antenna. What would it take for them to get in touch with us at 1,000 light years? They'd need a 6 megawatt transmitter, 6 million watts. That's not much. I mean, the Arecibo antenna has a radar on it, and I think it's either 1 or 2 megawatts. I think it may be 2 megawatts these days. It used to be 1. In other words, it's very close to that number. In other words, what I'm telling you is that even with the kind of technology we have, you could establish this communication link even over 1,000 light years distance. Okay? However, there's an insect here in the ointment because I've assumed that they have an antenna aimed at us and they're just, transmitting away. Now, why would they be doing that? And they have to be doing it for a long time because, remember, when we go down, we look at some star system, we might look at some star system over here 3 years from now, and we'll spend, like 3 minutes looking at it at a given frequency. Right? 3 minutes. The aliens get 3 minutes to get in touch from that star system. So in order to have any chance that we're going to hear them, they've got to be beaming their signal at us for a long time, typically thousands of years. This is the Drake equation, but that's what they have to be doing. So here's an alien. It was pointed out to me that his hands are not great, but in any case, here's an alien. So you have to ask, are they going to do that? Are they going to beam a very powerful signal at us for thousands of years? Because that's an assumption in what we do now, right? Or it seems to me that it is. And I'm somewhat doubtful that they would be willing to do that because they don't know we're here. All right, now here's I Love Lucy, of course, which I think was first broadcast in 1953. I think it was 53. So that's what? That's 57 light years out, those early episodes. Okay? So you can work this out that, I Love Lucy is washing over another star system at the rate of about 1 a day, which you'd think would make the advertisers happy, but, they might not like Fred Mertz's jokes or something. Okay, but that's still, it's only, 50-some light years out, and we haven't been broadcasting too much before that. Well, that means that anybody who's responding to us now can't be more than half that distance because, you want to see the response. And within the distance of the signals that we've been sending out, within half that distance, there are only a couple of thousand stars. Only a couple of thousand that know we're here. I think you can safely tell your neighbors that nobody knows Homo sapiens exist, except maybe domesticated cats. Nobody knows that we're here, right? So when your next door neighbor, tells you stories of how they're being hauled out of their bedrooms at night by little gray guys who are, doing things that their moms wouldn't approve of, you can say, gee, that's remarkable that they've come all the way here to do that because they don't know we exist. Just unlucky for you, okay? All right. You might say, oh, yeah, but maybe they found some other signal. Well, the facts are our city lights have not reached them either. To find our city lights, by the way, is very hard. You might work out how big an antenna, or rather a telescope, you need to see the lights of Earth from a couple of hundred light years. It's big. It's like an antenna about the size of the solar systems, or a mirror that's big. It's very big. The chlorofluorocarbons in our atmosphere that would tell them that we have refrigerators, that information hasn't reached them. Smoke, smog, the CO2 in the atmosphere. The aliens are always coming here to save us from ourselves. Right? Why are the aliens here now, Bob? Well, because they're unhappy about what we're doing to the environment, and also they're worried about nuclear war. Well, doggone it, they don't know about any of that stuff, right? And so, if they're here now, it's not because they knew about that stuff. It's like, you going to save the hippos without knowing about the hippos. Okay, so, it doesn't make too much sense to me that they're going to be relentlessly targeting us with a very big antenna with a lot of power. But you could say, yeah, that's okay. Maybe they're really broadcasting. Maybe they're transmitting a signal that just goes to everyone, like KGO, right? Maybe they're doing that. So they got maybe they have a big transmitter down in the center of the galaxy because after all, it's that's the place to go, and it's just belching out used car ads, as I suggested, or maybe join our book club, whatever it is, okay? And we'll pick that up. Well, that's maybe not a bad idea. We should look at the galactic center. That's the one special place in the whole galaxy, after all, the one very special place. I always think of, when Captain Kirk is beaming down some guys down to some godforsaken planet, I'll beam them down, I'll see you down there. What do you mean you'll see me down there? I don't have a map of the place. They can always beam to the North or South Pole. Everybody knows how to find those. In the galaxy, there's only one unique place, of course, and that's the center. So maybe they're broadcasting everywhere. All we have to do is look at the center of the galaxy. As I say, a good idea. However, you can work out the numbers. In order to produce a signal that we could detect with our present SETI experiments, looking at the galactic center, would require that their transmitter have a power of 5 times 10 to the 17 watts. That's a 5 followed by, 17 zeros there. That's a big number. In fact, that's more than all the sunlight falling on the Earth. And indeed, to put that in perspective, if you work that out in kilowatt hours, right, that's 10 to the 18th kilowatt hours, that's what it worked out. And you pay here to PG&E for a kilowatt hour, you pay about 10 cents. And they're trying to give you the cheapest electricity they can. They do it by doing things like burning coal and natural gas and so forth. They try and make it as inexpensively as they can. So at 10 cents a kilowatt hour, this transmitter, to produce a signal that we could find here 2/3 of the way out in the galaxy, would cost $1 billion a year, okay? Now, I never begrudged the aliens, money or energy or things like that, but that sounds like a lot to me. $1 billion a year. Sounds improbable. Okay, so the idea of a galactic beacon saying join our book club or whatever, centered at the middle of the Milky Way, you could do it, but it's extraordinarily energy expensive. Okay, so summarizing this little argument so far, I don't think they're going to be targeting Earth relentlessly with a signal because they just don't know we're here. Okay, and on the other hand, while they may be broadcasting to the entire Milky Way, maybe there's a galactic GPS system, right, or something like that. Maybe the weather report for the Milky Way, right, is being broadcast. The facts are that to do it at a level that we could detect is very expensive. So where are we? How do we deal with this? Well, we could, I say be smarter. I'm not sure that it's smarter, but we could think of some other ideas. One way to do that is to simply say, look, it's not going to be that strong a signal, right? Because the 10 to the minus 25 watts per meter square, which is the number I gave you at the beginning, as that's how sensitive our experiments are, that's what we can do 100 years after Marconi. We just invented radio, right? Now, the aliens, they may assume that the invention of radio is as far in our past as, the invention of the wheel. And, you probably don't remember who invented the wheel. His name was Rodney, by the way. But, you don't remember much about that story, and yet you use the wheel every day. And they may, you know, if they're 10,000 years ahead of us, they're not going to assume that our radio technology is at the level that it is. We will clearly have done much better, and consequently, their transmitters will be more attuned to what they think is reasonable at this end. And they may consider antennas that are measured in tens, hundreds, or even thousands of feet as not particularly reasonable. Well, are we going to be able to build a receiving system that can do much better than what we do today? Well, quoting Yogi Berra, I think Yogi Berra said, it's tough to make predictions, especially about the future. Actually, it's also possible that it was Niels Bohr who said this, but, you know, Niels Bohr, Yogi Berra, what's the diff? Let's see if we could go for weaker signals. Well, this is one way we can go for weaker signals, building bigger antennas, and of course we're going to do that. This is an artist's rendition of the square kilometer array, which will have 10 times the collecting area of the one down in Puerto Rico. So that's pretty big. And with something like that, you could obviously push the power requirement at the other end down by a factor of 10. So instead of $100 billion a year of electricity, it's only $10 billion of electricity. I don't know that that helps a whole lot. But I point out that there's an interesting aspect to this kind of technology. Radio antennas of the future, radio telescopes of the future may not have these, you know, dishes. They may not. But when you have a dish, you know, a physical 3D structure like that, then the cost of each antenna goes as any dimension cubed, obviously. Okay, but if you have flat antennas, and it may be possible to do these all as some sort of substrate, and you just have a whole bunch of dipoles on the ground, then the cost per element only goes up as the square of any given dimension, and that might be a real win there. But in any case, here's sort of the bottom line on all this stuff. What I've done here is I've just taken a bunch of my favorite radio telescopes and plotted them on this plot as to how much collecting area they have. And so this was, you know, one of the first ones built by an amateur, Grote Reber in Wheaton, Illinois, back in the 1930s. And there's a square kilometer array. You know, that date is more or less there, but you can shake that thing around. And you can see some other telescopes in there. Now, the point is, they're getting bigger. At least on average, they get bigger. The biggest ones get bigger. And this is a least squares fit plot there. And you may or may not believe it. But what it shows is that over the course of 100 years, the antennas have gotten about 100 times bigger. Okay, so, you know, every 100 years, every century, you get 2 orders of magnitude improvement. Now, you may not believe that, but that seems to be the case. I'll give you an optical example. On Mauna Kea in Hawaii now, Caltech and others are building the 30-meter telescope. Okay, they haven't actually broken ground on it, or maybe they have, but, you know, most of the ground is still there. 30 meters across, a mirror 30 meters across. For comparison, 400 years ago, Galileo built a telescope with a 3-centimeter aperture. In fact, it was probably smaller than that because in the old days, they would stop the lens down, you know. In other words, that's a factor of 1,000,000 improvement in size in 400 years. Right? So that's 6 orders of magnitude in 400 years. That's not too much different than 2 orders of magnitude in a century or so. I mean, you know, so you get orders of magnitude improvement over the course of a few centuries. Right? So that suggests that when we get a little bit farther down the line here, we could build an antenna that was big enough to find the kinds of signals that would be pretty cheap to broadcast to the entire galaxy. Okay, this is an example with the square kilometer array, but you could get down to this sort of sensitivity, and that means that the aliens would be able to broadcast a signal we could pick up with only 10 to the 13 watts. And 10 to the 13 watts is still a lot. That's 10 trillion watts. But actually, humanity consumes somewhat more than that already. So, you know, it's now getting to a level where you think, you know, a really advanced society might be able to afford something like that. So that's one way to do it. We just sit around for a couple of 100 years and then do the experiment again. Needless to say, this isn't very interesting, okay? But the other possibility is to do what's actually proposed here, and that is to take an antenna, the bigger the better, and just aim it all the time at the galactic center, for example, for a year and just beat down the noise. You would gain a couple of orders of magnitude over current limits if you did that. And maybe that's enough to give you success, and maybe not, but it strikes me as something that's worth trying. In other words, a very highly sensitive search of at least one spot on the sky, and that spot on the sky I would think would be the galactic center. By the way, this harkens back to the idea of Barney Oliver, known to many of you in the audience. He was the R&D director at Hewlett-Packard for its first 20-some years. Barney Oliver was in the 1970s proposing that we ought to build a huge array of antennas to try and find ET. But, you know, unfortunately, you have these artist impressions that sort of scared everybody off because that looked expensive, okay? And I'm sure, well, in fact, it was expensive. There were, you know, these billions of dollars. But on the other hand, that's sort of misconstrued what his idea there was. His idea was, look, you build one antenna, and you do the experiment. And if it doesn't work, you build 4, and then you build maybe 16 and so forth. That you just keep building it until it works. And that way, you never build more than you need, okay? Which I thought was a clever approach. Hasn't been done. Okay. Here's another way we might approach SETI. This is just, you know, to get your creative juices going. Special cases. I like special cases. This is an idea that goes back a ways, primarily espoused by Guillermo Le Marchand, who is an Argentinian astronomer and physicist. And here's the way it goes. It turns out that, although he wrote a lot of papers about this, it turns out that 20 years earlier, the Russians had already thought of it. But actually, when you look into any idea in SETI, it turns out that the Russians had always thought of it earlier. And, you know, the interesting thing about that is that it's usually true, too, by the way. They really did. They were very clever. I think the Russians didn't have a whole lot of money for equipment, so they would sit around with pencils and papers. And they were very smart. Still are, actually. Okay, so the deal is, suppose some supernova goes off, you know, in our galaxy, nearby galaxy. Bam, big explosion. Right, well, the astronomers, here's some alien planet there. Right, so the astronomers on that alien planet, they wake up. They go, wow, like supernova. And, you know, that means we can get maybe, you know, some PhD theses for the grad students here, whatever. Maybe I can get tenure if I write something up. So all the telescopes on that world are aimed at that supernova for a couple of days or a couple of weeks. They study the heck out of it. But one guy, you know, is clever enough to say, wait a minute. And he waits half a day, and he just sends a signal out in the direction opposite to the supernova. Okay? Now, here we are on Earth, and at some point, you know, who knows what that signal is? You know, hi, we're the Klingons, and we'd like to meet you. Okay, so here's Earth, and at some point, you know, the supernova lights up for us. Hey, whoa, supernova. So every antenna, every telescope in the world is aimed at that supernova, and, you know, 12 hours, 15 hours, 20 hours, whatever a half day is for the aliens. Later, after we start studying it, we get this message. It says, hi, we're the Klingons. You know, want to come to our parties. Okay, so this is pretty nifty because it tells you when to look and where. You don't have to, you know, just have long, long lists of star systems to look at. You just look at a supernova whenever it goes off. Okay. The trouble is, of course, there aren't that many supernovae going off in our galaxy. And in other galaxies, it's a little unclear whether it's big enough to get anybody interested. But this is a clever idea. I think it's a very clever idea. Here's another idea. I floated this idea years ago at a conference in Italy where it got essentially no notice. And since then, it's been ignored. But here it is. It turns out that on the basis of theoretical calculations, you could have planets around double stars. Now, about half of all stars, 60% I think is an actual better number, are multiple stars. Stars, you know, like to have buddies, and they have, many of them do. Okay, and you can have planets around these buddies if either they're very close together, so the planets go around both at once, or they're separated by not very much, maybe the distance from where you are to Saturn, which isn't a whole lot, and you could have planets around both of those things. Okay. In fact, we found planets around double stars. That has happened. Okay, but well, if you can imagine some society growing up in a system like this, and maybe you grew up on a planet around this lower star, you would, as soon as you invented rockets and radio, all of which are sort of contemporaneous, right? You invent radio, and then within 50 years you invent rockets, and then you invent the H-bomb. All these things happen at the same point, right? So just when you go on the air, you blow yourself up. But, okay, so that's a different story. So you're on a planet around this guy, and very quickly you colonize some of the planets, assuming there are any, or just build satellites around that star, because a second star could be useful for you. Get some energy out of that. Who knows? Just study it, right? And that means now you've, in some sense, your society extends over both stars, and they will communicate, right? There'll be communication back and forth between these two star systems. Now, imagine the situation, and this obtains for one in a couple of hundred of such stellar pairs, that they're seen kind of edged on. And they become what are called eclipsing binaries. You can see the animation of an eclipsing binary over there. And here are actual observations of an eclipsing binary where you see this star, you know, get brighter and dimmer because, you know, the big star, which is kind of dim, gets in front of the small star, which was kind of bright. A small star is a white dwarf in this case. Doesn't matter. And you can see the light curve here. Okay, so these are called eclipsing binaries. You don't actually see the stars going around one another, but you know when one gets in front of the other because suddenly the light goes away. Okay? Well, all you have to do is say when that happens, you're looking right down the communication pipeline between these double star systems. So again, this tells you when to look and where to look. hasn't been done, but I think it's maybe something worth considering. Here's another idea, and this has also been proposed. There was a big fight about whether we thought of it first, or some guys at NASA had thought of it first, and then it turns out that the Russians had proposed it 20 years earlier. But the problem is that nobody reads the Russian literature, I suppose, except the Russians. But this is a piece of art by Lynette Cook here in the Bay Area, showing a planet transiting a star. We know about many of these now. But imagine for a moment that this is the Earth going in front of the sun. So, this is what Kepler's looking for, of course, transiting planets. But imagine that the aliens had their own Kepler project years ago, and they found the Earth that way. Right? They just happened to be in the right parts of the universe that they would see the Earth cross in front of the sun, so they know that there's Earth there. And, maybe they said, well, it's kind of a rocky world, and we can measure a little bit of oxygen in the atmosphere, so maybe it has some life. Why don't we occasionally give them a ping and see if they'll join our club, okay? So maybe what they'll do is they'll say, look, we have to figure out when to broadcast to them. We don't know that there's any intelligent life there, but we'll broadcast to them sometime during the transit, which takes a couple of hours in the entire year. The Earth takes a year to go around the sun, and for a couple of hours, it'll block the sun from their point of view, okay? So all we have to do then to get in touch with the aliens is examine the ecliptic. We just look at the path of the sun through the sky. We move the antenna 1 degree every day, right? So there goes the sun around the ecliptic. We're looking in the anti-sun direction, of course, right? And expect their signal to come in, wherever they are. When we're transiting the sun, they will time their signal to get to us when we transit the sun as seen from their star. Now that requires that they know the distance from where they are to the sun fairly accurately, but not in unconscionable accuracy. It's a kind of accuracy we might have in 100 years. So again, tells you where to look. They know when and where to transmit. You can't read this. If they target the sun, by the way, if they're good enough, if they have big enough arrays that they can do that, it doesn't cost much in the way of power. Here are the alien transmitters over there, and their beam, whether it's a light beam or a radio beam, just covers the sun. They know we're somewhere in that disk. Then, they can send us 100 bits per second with only the power of an automobile headlamp. Okay, so that's pretty cheap. Okay. We don't do this either, but it seems like an easy thing to do, because all you need is an antenna about 25 meters across, an 85-foot antenna, something like that, and you just look at the anti-sun direction all year long. Trivial. There are plenty of 25-meter antennas around. Okay, you could look in the infrared. We don't do this either, but this is a matter of economics. And the reason to look in the infrared, I pointed out Shelley right here looking for flashing lights from the sky, but those photomultiplier tubes that are doing this, they're just sensitive to the kind of light that your eyeball is sensitive to, ordinary light, the few photons in this room here, okay? But ordinary light, it's great for a lot of things, but it's not maybe so good for signaling over long distances in the galaxy. This is just a picture of the Milky Way at night here, and a little bit of earthly topography. But you see all these dark clouds. There's all this dust in the Milky Way, in the plane of the Milky Way. And what this does is it makes it very hard to signal over distances greater than on the order of 1,000 light years. Depends on where you are and which direction. But on that order, if you're trying to signal farther than that with ordinary light, it isn't going to get through. It's going to get blocked by all that dust. Okay? So, but not in the infrared. Infrared goes right through the dust. Okay? So, doggone it, all we need to do is have a optical SETI experiment in the infrared, and let's look for things. And the problem with that is the infrared doesn't penetrate the atmosphere. So in order to do this, you have to move the experiment into space, or maybe the backside of the moon or wherever. And that's too expensive at the moment, but it's a very obvious thing to do. Okay, here's another idea. SETI is, SETI experiments, we're looking for a signal in space, but we only look at one little tiny patch at a time. It's kind of, like looking for comets. Now, you don't use the world's biggest telescopes to look for comets, because they're looking at a little tiny patch of the Keck telescope will never find a comet. Comets are found by amateurs, mostly in Japan, it seems, with binoculars. And they get up very early every morning, they know where to look. Okay. Because you need to scan a big part of the sky. Well, maybe there are all sorts of big signals coming from ET, just a ping once every year in that direction, big blast of radio waves, and we never see it because we're not looking in the right spot at the right time. I mean, that could be. If they just once a year made a big ping in any spot on the sky, you would say, I don't know what it is, Bob, but there's something very weird in that direction. And you would spend whatever money you had to examine that spot on the sky. And then you might find a very low-powered transmitter that was, giving you their version of their encyclopedias or their internet or whatever it is. Okay. But we have no way of finding something that's going off, intermittently in some part of the sky because we don't cover enough of the sky at once. Well, here's one way you could do that. You could use the moon as a garden ball. You know those silver garden balls? You put them I don't know how many of you have those anymore. If you have the storks in the front yard, probably don't have those either. Okay, but it's one of these garden balls, these silver garden balls. And the deal is, if you look at this thing, you see the whole sky, right? And you see your neighbor's house and all that. So you see everything. It's a really, really fisheye lens. Okay, well, the moon works that way with radio waves. So the radio waves come in from at least half the universe. They bounce off this thing. And, of course, unfortunately, they get scattered in all directions. But some of them get scattered back toward your telescope. So by looking at the moon, you're looking at least half the universe. Okay? Now, because of these geometric effects, of course, your sensitivity is down by a small factor, 50,000, 100,000. But, what are 5 orders of magnitude when you're talking about aliens? Because if it was a really honking signal, one that, would just about fry your toast, then this would work. And again, the size antenna you need for this is, again, on the order of 25 meters, at least at the kind of frequencies that SETI usually uses. So you could just cover the whole moon with this thing and just follow the moon. In fact, you want 2 of them, right? The moon tends to set. So you have one on one side of the Earth, the other on the other side of the Earth, and you just look at it all the time. Look at it all the time. Just in case, just in case. Okay, here's another scheme. This is a spectrum of the Earth as seen from space. Now, you notice a couple of things in the spectrum. This is just a distribution of the light. This is kind of a rainbow of the Earth. And you see it has oxygen, better known as ozone here, carbon dioxide, things like that. These are indications of life, not so much the carbon dioxide, but the oxygen is. Right? The oxygen in the atmosphere here, to the extent there is any after you've been in here for a while, the oxygen in here is due to plants. You know that, right? Mostly, bacteria, blue-green algae, as they're called. There's also methane in the atmosphere here, which you could detect in space. And the methane is due to what's politely called bovine flatulence here on Earth, also porcine flatulence. So this is a way to find pigs in space, if you find methane in somebody's atmosphere, right? Okay, so this is another way to be smarter in this sense. They may have done this experiment. We haven't done this experiment with other planets really to speak of, but they may have the instruments that we'll have in 20, 30, 40 years to be able to get really good spectral information coming from planets around other stars. And the point is, this signal from Earth about the plants has been going out into space for 2 billion years. Right? That's when the oxygen began to build up on Earth's atmosphere. At least that's the best number. Okay, so for 2 billion years, we've been broadcasting to space, not I Love Lucy, that's only been the last 50 years, but for 2 billion years, we've been broadcasting, hey, Earth has plants. I guess the fact that the aliens aren't here says that there aren't too many alien vegetarians. Maybe that just occurs to me now. But okay, all right, so they know about our plants. Now, knowing about our plants, might be interesting for the botanists among the aliens, but it doesn't mean that they would send any signals our way because, after all, you could have aimed signals at Earth 300 million years ago. We had a lot of plants. There was plenty of oxygen in the atmosphere, but there was nobody to pick up. I mean, the trilobites were not big in radio technology. Or if they were, they hid all the information. So you could just because you find that a world has life doesn't mean that it has intelligent life. We've had close to 4 billion years of life on this planet, right? And only in the last 100 years has it been technological. So just because you find a lot of worlds that have oxygen in their atmosphere, whatever you consider the spectral signatures of life, doesn't mean, now we know where ET is. No, now you know where maybe trilobites are, bivalves, or in any case, ferns. Okay, but this may suggest a strategy for them because they may have done that. They may have done this experiment so thoroughly that they have hundreds of thousands of so-called bio-worlds, right? They've got a long list of these things, and we're on it. We're on this list of worlds known to have biology, or at least plants, okay, which you consider biology, right? Okay, and maybe those lists are very long. I'm being optimistic here that that life is not a miracle of some sort or, very, very exceptional. Then there will be large numbers of worlds that have biology, and they may have long lists of these, and they may say, well, we don't know which of these have intelligent life, but these are at least worlds with life. Well, so why don't we try and get in touch with them? But we can't spend a lot of time on each one. because each one has a pretty low probability of having a life. So maybe they just ping them sequentially. Here's an example, a real numerical example. Suppose ET pings 1 billion targets. They found 1 billion of these. That's a big number. Over and over and over again, you know, every 3 days or whatever it is. They just go through the whole list again. They send each of them just a 1 nanosecond ping. They do this with light, say. All right, 1,000 photons per second, so per meter squared. That would be an easily detectable signal even for our experiments today. So every couple of days they do this. If they have that kind of duty cycle, then the repeat interval is 3 hours. So every 3 hours, you would get a ping from these guys. Every 3 hours, big ping. Okay? And again, that would tell you, well, you know, there's not much information in the ping, but there is this information in the ping. It gives you a spot on the sky. You know, they're there. There's something funny there. And then you would, again, you know, you put all your grad students on it. Okay. Now, to do this, requires a 5 gigawatt laser, which is pretty powerful. But again, that's something we can build. So this isn't so much of a demand on the aliens. So what this suggests to me is that maybe if ET is really trying to get in touch, aiming big antennas at the Earth all the time, this doesn't seem to me as reasonable as maybe a 2-tier transmitting strategy where they just first try and get your attention with a ping, right? And that just means you're on a list, okay? And then they have a low power, always on transmitter that has all the information. Right, that's just always on, regurgitating the information over and over again. Remember, if ET is hundreds of light years away, 500,000 light years away, we're not going to get in conversation. I mean, it's going to be very tedious, right? You finally hear from these guys, so you send them a response, hi, we're the Earthlings, we'd like to know what you look like and whether you have rock and roll. Okay, and you send that, and it takes 500 years to get there, and if they deign to reply, that's another 500 years for the response, and then they come back and say, you know, please repeat that, or whatever. So that's tedious, right? It's going to be one-way communication, essentially one-way communication. And I am fond of pointing out that I took Latin in high school, and we had one-way communication with Julius Caesar. He was talking to us and not the reverse. Well, the kid next to me was talking to him, but Julius was not listening to him. So it's one-way communication, but it's still interesting because, after all, Julius had something interesting to say. So the aliens may have something interesting to say, but the point is that they did, you know, that's the low-level transmitter because it's cheap for them. But now they got your attention with the ping, so they don't have to spend a lot of money on the low-level transmitter. So here's the logic. I haven't talked too much about this, but as technology improves on our planet, we're not belching big signals into space anymore, right? The Sutro Tower is doomed. You're going to get your television and your internet via a fiber optic or some other way, and the aliens are already there. So I don't think we're going to pick up the accidental radiation that comes off their planet. Could be, but you know, it doesn't seem so likely. So I think we should expect some sort of deliberate broadcast, deliberate transmissions. But they don't know we're here. They don't know Homo sapiens is here, but they do know there's life on this planet. So we're just in a list, and the list has to be long to be interesting because the chances that any given planet with life also has intelligent, technologically competent life isn't so good. So they'll do these intermittent short pings. So I think that, you know, we should at least consider some aspect of our SETI strategy where we look for very short pulses, right, either in the optical or in the radio, with reasonable repetition rates. Okay, they may not send us a signal that's always on. Let me just sort of conclude this soporific presentation by going into something that I think may be relevant. And I often talk about this. I title this Beyond the Grays. This is sort of the impression we have of what the aliens will be like, of course. These little gray guys who obviously have no sense of humor and not much dentition, who sit around. And as I point out all the time, these are merely projections of our future. This is what we're going to become because, you know, we're losing our hair, but these guys have gone way beyond that. We're losing our olfactory sense, so their noses are pretty small too. And, but the only thing that's gotten bigger are their eyes because in the future, your job description will be design websites. So this is your descendants right here. That's, you know, and this is the way I think many of my colleagues, I think many people in science in general, if you ask them what are the aliens like, they start giving a laundry list of things about us, really. You know, carbon-based life forms, carbon-based life forms, Captain. And you know, that makes sense. Carbon works better than anything else. But, you know, homochirality, they've got either left-handed or right-handed molecules, plate tectonics, big moons, big planet around to chase away asteroids, bigger than rats, smaller than 10 elephants. They have to have something to pick up a soldering iron, otherwise you don't hear from them. A lot of people tell me, you know, the dolphins are really smart. Well, they may be, but they're not building radio receivers or transmitters. And I figure the reason is if you try and hold a soldering iron in your beak and use it underwater, it doesn't work. Okay, stereo vision, sanctuary. Okay, this is the assumption about what ET is going to be like, and then there's arguments, oh, well, they have 4 appendages or 6, or, you know, will their brain be up here, down there, whatever, that kind of stuff. But of course, I think this all misses the point, and the point is, given by this plot here, my favorite plot, by Hans Moravec at Carnegie Mellon Institute. It's 10 years old now, so we ought to fill in some data up here. But anyhow, it just shows the amount of compute power you can buy per $1,000 ever since 1900. Okay, it's going up, and those of you who are still conscious may have noticed that this is a semi-log plot, which is to say it's going up exponentially. It's a highly overused word, exponentially. You hear it every morning on the news, you know, exponentially, but I'm sure the newscasters have no idea what it means. But anyhow, this really is exponentially, so you can feel confident that you won't be exposed. Anyhow, the point is that by 1997, for $1,000, you buy the compute power of a spider. Not so interesting unless you're an arachnophile. Today, you know, following the curve up here, you buy for $1,000 the compute power of a lizard, which might be interesting if you're trying to sell car insurance. Okay, so, but the real point is that by 20, it's bad when I find my own jokes funny. I just, fortunately, almost never happens. By 2020, right? By 2020, your laptop has the compute power of you, right? Now, this is being pointed out by lots of people now, okay? And there's very little doubt about this unless, you know, there's some sort of nuclear implosion or something like that. This is going to happen. And the usual question is, so what happens then to us? And, you know, some student at the University of Washington said, they'll kill us all, right? And that's, I explain that as the natural optimism of youth. I said to the student, you know, look, I have some goldfish at home, and I'm smarter than they are, but I don't wake up in the morning saying, got to kill those guys. Never occurs to me. My personal plan is when this happens, I'm just turning the keyboard around, you know, you type, whatever. Okay. Now, the deal is that doesn't mean that they're as smart as we are, of course. All it means is that they can do as many, you know, computations per second. We have big, massively parallel brains, but in the end, you know, the software may catch up, and maybe they will be intelligent. I mean, the Silicon Valley is the home, John McCarthy is here in the Silicon Valley, the home of artificial intelligence. And the artificial intelligence community, bless their hearts, have been saying for 30 years, we're going to have a thinking machine within 10 years. Okay. And of course, they're well aware that there's some disconnect here, but they will tell you, don't confuse lack of success with lack of progress. There is progress. So I have no doubt that it'll happen. A lot of people do have doubts. They say, you're never going to build a machine that can teach high school chemistry and deal with the students too. Right? They'll say that. But that's assuming there's something miraculous going on between your ears. Now, I don't know about yours, but I know there's nothing miraculous going on here. Right? If you ask people, could you make an artificial heart? You bet. Could you make an artificial kidney? They got them. Artificial liver? Yeah, that sounds right. Artificial pancreas? Don't know, but maybe you could do it. But somehow when you say, well, what about that organ between your ears? Well, that's sacred, man. Can't do that. Right? Philip Morrison, who was important in the first days of SETI, of course, described the human brain as a slow-speed computer operating in salt water, which I think kind of gives you a better perspective. Anyhow, okay, so if you can do this, and the point is, once you do it, maybe you don't do it by 2040 or 2050. Maybe it takes to 2100. So what? Doesn't matter. 2200 still doesn't matter. As soon as you've done that, within 30, 40 years, that single machine now is better than all humankind put together. Now, my point here is not to, you know, concern you that you may be the last generation of hominids to run the planet, which I know many of you will take as an incentive to adopt a hedonistic lifestyle. I think many of you have already done that. Let me make that point. I like this guy. I made this graphic up from a bunch of stuff I found on the web. But I think that it's sort of instructive, again, to understand that this is a time scale argument. Right? Here's a horse 60 million years ago, right, when they were about the size of a collie dog. Here's a horse today that you can find in, for example, Portola Valley, and it's about the size of a horse. Okay. Now, that's 60 million years. Okay. Now, on the other side, you have personal computers. I had a personal computer in 1977, and it had a 1 megahertz clock rate, and I think an 8-bit bus. Right? It was an 8080. So 8-bit bus. My computer at home now has a 2 gigahertz clock rate, and I think it's 32-bit bus. So that's, what is it? That's 4,000 times, no, 8,000 times better. 8,000 times faster. So 8,000 times faster in 30 years. On this side, collie dog to horse in 60 million years. You get the point. Darwin is not only unpredictable, but it's really slow. It's slow. It can make some changes quickly if you're a fruit fly, but if you're talking about intelligence, right, our IQs may not really be any different than they were in the Roman Empire, let alone maybe not even in the days of, when we still shared the planet with Neanderthals. So that's slow. This is fast. So once you develop this in artificial intelligence, assuming you do it, then it quickly swamps Darwinian evolution. Okay, so here's the argument. Oh, people say, but that's okay. We're going to put chips in our brains. Of course we're going to do that. I have friends that already have chips in their brains. And we're going to become like the Borg. We're going to be half human and half machine, right? And we're going to improve on this silly molecule over here. That we're sort of going to keep up with the machines because we're going to take advantage of machinery ourselves. Well, undoubtedly we will do this. I don't doubt that we'll do this, and this will be very interesting for you personally. But to me, this is like putting a 4-cylinder engine, into a Greyhound. You get a faster dog, but in the end, you say, let's get rid of the 4-cylinder engine and or rather, get rid of the dog part and just, build the Maserati or whatever. Okay. So, although I think that this will happen, it's just transitory and can't possibly keep up with the machines. Okay. So here's the timeline argument. Somebody made this plot. Here's Homo erectus. These back and forth curves are because they didn't want to draw one long line. But they just some sort of time scale indication, how long we spent, sort of ambling through the forest on 2 legs, eating, whatever we found, and not leaving a whole lot of great literature. And then, then at some point you get Homo sapiens, whose brain is now 3 pounds, doing a little bit better. The little dot up there, that's all the time since the invention of the steam engine. The thing is, things happen very fast at the end here. So here's the point. You invent radio so that you go on the air, right? Within a century, 2 centuries, maybe 3, probably more like 2, you invent your successor. So the time in which the aliens spend as little soft, squishy gray guys is very short. And consequently, if we find them, what we're much more likely to find than those gray guys, right, are some sort of machinery. I mean, I think you can forget this guy, although I like him because he had the same plastic surgeon as Michael Jackson there on his nose. This was from a film that I actually enjoyed, The Arrival. It had the bad form to come out, 2 weeks before Independence Day, so nobody went to see it, but it was actually pretty clever. Anyhow, very anthropomorphic alien. This is great. Hollywood loves anthropomorphic aliens, but I just don't think you should take that terribly seriously. Now, what are the machines going to do? Because maybe it comes down to this. How can we second-guess the machines? Where are they hanging out? What are they doing? How can we find them? Because our SETI experiments might have more luck looking for the long-lived kind of intelligence and not the transitory intelligence that is biological. Well, Ray Kurzweil was at the SETI Institute a couple of months ago, and he said they're all going to, they're going to build nanobots, and the nanobots are going to, swarm through space. Well, there's a problem with that. As far as I can tell, they haven't been doing that. I mean, maybe they have. Maybe that's why space is so empty. Maybe the nanobots have eaten it all. But, really, this doesn't make sense to me. If you want to maximize intelligence, you really want to keep things compact. Otherwise, you have time-of-flight problems. It takes too long for information to get back and forth. This also leads to gray goo. Maybe the aliens are turning everything into gray goo somewhere. But this is much more likely that you just have very compact, very compute-intensive entities, right, that are sitting around. And I don't know what they do. I mean, people will ask, so what are these guys interested in? I really haven't any idea. I mean, maybe they're sitting around playing free cell all the time. It's hard to say. You would think that they would have some curiosity about the universe, and you would think that they would ultimately be concerned about the fact that the universe will run down. That's a problem that they will have, too. But that problem's far into the future. I think it's rather hard to speculate on what their sociology will be, despite the fact that I get emails and phone calls every day with people telling me about why the aliens are here abducting their neighbors. This is all alien sociology. And for alien sociology, the data set is sparse. So if it's sparse for the little gray guys, you can imagine that it's sparse for things that are completely different than we are. One of the gentlemen in the audience, in fact, Mark pointed out to me that I ought to read a book by Stanislav Lem, a short story called The Golem 14, in which they invent a thinking machine, which I did, by the way. I read it thanks to Mark. And there, the machine, he sort of interacts with the humans for a while and helps them solve some problems here and there. But then he gets really bored with the whole thing, or who knows what happens, but he just shuts himself off. It's sort of like, you get tired of the goldfish after a while and you walk away. Okay, so maybe that's what happens. But anyhow, if you want to answer this question, you got to say, is there anything you can say at all? Or is there nothing you can say? It's entirely speculative, all of this entirely speculative. There are, if I ask you what's really important in life, right? The young people here will all say sex and money. But in fact, it's really matter and energy, which on Earth we turn into sex and money. But it's matter and energy, okay? Because they presumably will need both, right? Okay, if they want to keep up. All right, so let's consider where there's a lot of matter and energy. Well, one place I've already mentioned, this is the galactic center, seen in infrared. There it is down in there. We've already talked about that. The other places where you find a lot of matter and energy are where new stars are being born. You get these hot stars like O stars. You know, fewer than 1% of all stars are O stars, but O stars are very much hotter than the sun. They can put out 100 to 50,000 times as much energy as the sun. So if your gusto-grabbing, free-living lifestyle requires a lot of energy, you want to hang out near one of these bright stars. Now, mind you, they burn out in 10, 20, 50 million years, but maybe that's good enough to have fun. Okay. Molecular clouds, they have hot stars and lots of material. Okay, here's one, the Taurus molecular cloud. Here's another one, the Orion cloud, which you can see tonight, the pair of binoculars if it hasn't clouded over again. And there are knots of material in here. Radio observations have shown that. Things that have, like a few percent or 10% of the mass of the sun in a fairly small amount of volume. And that's a lot of material. That's 100 times all the mass in the solar system. So if that's of interest to you, if you have big building projects and you need a lot of energy, then these are the kind of places you might go, and you might, in fact, be making your presence known. This is, again, speculative. Why would they broadcast? Not sure, but one thing that they would want to know is who else is out there. And unlike, biological intelligence, machine intelligence could actually, converse with one another in a sense that they might be able to improve one another. Conceivable. Black holes. Roger Penrose in the UK, there's a black hole up there, has suggested that, maybe they hang out around black holes, or he didn't really suggest that, but maybe our descendants should hang out around black holes because you can get a lot of energy out of a black hole. What you can essentially do is by throwing your garbage around the black hole and that kind of thing, you can extract the angular momentum energy of the black hole. You need a spinning black hole. Okay. And by the way, the angular momentum of the sun, I worked it out, is like 10 to the 36 joules. That's a lot of energy. So, if you have a black hole that's made from a star about the size of the sun, 10 to the 36 joules will keep a society like ours going until the last star has burned out, right? A long, long time. So, maybe they've gone there. I like these guys, these so-called Bok globules, because Bart Bok, famous Dutch astronomer, actually found these guys. These are just dark patches of dust and gas. They're typically the nice size to just cover with a radio telescope, too. And sometimes there's some bright stars nearby. But the real point is that these things are really cold. A lot of molecules there, 20 to 100 solar masses, a lot of material, very cold. Very cold might be interesting if you're a machine, because those of you who've taken thermodynamics know that a machine is much more efficient if it's got a good heat sink, if it's in a really cold environment. You want the temperature difference between the engine and the environment to be great. So these very, very cold places, which are only a couple of degrees above absolute zero, might be the places where some really clever machines are hunkered down. Well, then let me finish off here. It's been 50 years since Frank Drake, who comes into the Institute every morning and writes this equation on the board. A little unclear what it means. Keep meaning to ask Frank. Anyhow, 50 years. We haven't found a signal yet. And that may sound like a long time, but again, the total number of star systems that we've looked at carefully up until now is 750. So even if you think that's the best scheme, that's such a paltry sample, right? Such a small sample. To say paltry is to denigrate it. It was actually a lot of work by a lot of people. It was an incredible tour de force to do that experiment, but it's still a very small sample of the star systems in the galaxy, okay? We've just begun to fight, as it were. Thanks to new instruments like the Allen Telescope Array, we'll be able to speed up the search. And I've already suggested to you that if our assumptions about how many societies are out there are anywhere near correct, we may trip across the signal in the next 24 years. So it's the wrong strategy to give up. This is not the time to give up. This is the time, in fact, to get optimistic about the possibility of the future. I just show you this last plot just in case anybody still has their eyeballs open. These dots show you the speed, some metric of the speed of SETI searches since 1960. There's Frank's original experiment there. You see the red line is Moore's law, and you see the speed follows Moore's law very carefully. And with this slide here, this is a picture I made in June of 1997, and this is the basement of the SETI Institute when we were in our old quarters. This picture was made at 3:30 in the morning. You see Tom Pearson, our CEO there, Kent Cullors, the blind physicist in the movie Contact, was working there at that time. And we had found a signal that for a long time, 16 hours, looked like it had the characteristics that we were looking for. Very interesting. This really is 3:30 in the morning. I was so nervous, I couldn't sit down. I just had to walk around taking pictures because it gave me something to do. Right? Nobody went home. Nobody went to In-N-Out Burger. Well, there wasn't any In-N-Out Burger in Mountain View then. Nobody got, food. We just sat there and watched this signal. Well, that turned out to be a false alarm. That was the SOHO satellite, and it was largely due to an instrumentation problem that we had that we even thought it was real, but it was an extraordinarily good test run to show what happens when you get a real signal. What happens when you get a real signal is you stay up all night, and by morning, the media are calling you. The New York Times called me in the morning. They already knew about it. Hours into this, they already knew about it. You needn't worry that all this will be kept from you. It won't. They'll be writing stories about it long before we've confirmed the signal. That's for sure. You'll read about it first in the checkout line. That's my usual. And yes, you will. This hasn't happened yet, but I think it is likely to happen in this next generation. I bet everybody a cup of coffee on that. And I think that the other thing we might do is, although we've been doing Frank's experiment now for 50 years, there are other approaches that I've thrown at you, some of which I think may appeal to some of you, that I think we ought to try. Thank you very much for your attention.
Yeah, my question is, so a couple of things you pointed out in the talk were essentially looking at waste products. I Love Lucy broadcasts oxygen, which is really a waste product for plants. As you look at ideas about more advanced civilizations, this computronium idea, that kind of thing, has anyone ever given any thought to what kinds of waste products a civilization like that might produce and what you might look for to just see if they're leaving a trail of trash behind them?
Right. Did everybody hear the question? I'm not going to repeat it because there's a PA system here. I'm sure Desi Arnaz would thank you precious little for calling this long-running program a waste product. But you're right. I mean, in a sense, you're looking for the residue, and oxygen, by the way, is actually useful for us, if not so much for the plants. But somebody has, to answer your question, somebody has done that. There was a presentation I heard a couple of years ago, and unfortunately, I can't remember the guy's name. He was an economist, and what he did is he said, imagine there's a really advanced society, and they're kind of aggressive, and they just sort of sweep through big sectors of the galaxy. And what are they going to leave behind? They're going to leave, if you look behind Alexander's army, walking around Europe and the Middle East and into India, there was all this junk left behind, right? The remains of the encampments and the food and all that stuff, dead bodies, whatever. And so he tried to figure out, indeed, the answer to your question, what would be left behind. Unfortunately, I don't remember the answer to your question. But there was, among the things to look for were strange radioactive isotopes, because presumably they would have, of course, some form of nuclear power, and some of the obvious reactions were considered. And they all produce these isotopes that you wouldn't find in nature, right, in the abundances that you might find in the trail of some colonizing force. So that article actually is probably published somewhere. Send me an email, and maybe I can find it. But indeed, at least one person has looked at it. I think it's a good idea, although it's kind of disconcerting to think that we're looking directly for the trash. Over here, let's try this again.
Seth, you mentioned the movies, and indeed it is a great pleasure and honor to know you personally, and because of that I know that you like to watch really bad science fiction movies. Did you even bother to watch the recent wonderful science fiction movie that everyone is talking about, and what did you think? Thank you.
Which one was that? I'm sorry, I got everything but the title. Avatar. Oh, it's like a setup, Mark. Because I wrote a review of it. Yeah, you can read it. It's actually on the Huffington Post, but to find it on the Huffington Post is actually not so easy. The best thing to do is go to the SETI Institute website at www.seti.org. Right, go there, and you'll find a link to it. And I talk about it. I mean, look, there's so many things you could say about Avatar, and it just seems like a cheap shot to say most of them. But they live in a tree. Okay. By the way, I had dinner with Cameron once here in Los Altos. I committed a faux pas, and he nearly stabbed me with his fork. But I actually like the film a great deal. But most of the article describes the feasibility, and this was the premise of the film. I'm not giving anything away here, really. It involves a mining operation on a distant planet. Right, we go to a distant planet, Earthlings. We go to a distant planet to bring back unobtainium. which I thought was a singularly unimaginative but daring name for this stuff, unobtainium that was worth $20 million a kilogram. And all I did in the article is work out how much it costs to bring that back. And the bottom line of the article says, this is like ordering a book from Amazon, latest bestseller, and having to pay $60,000 for the postage. You probably wouldn't do it. And yet, and the reason I picked on this is because this is a very familiar trope in science fiction that will go mine somebody else's worlds. I don't think that makes a whole lot of sense myself. But the film was good, by the way. I commend the film to you, in my opinion. Okay, back over here.
Are there any plans to do very long-term searches of individual stars lasting months, perhaps years? And if you could talk about that a little bit.
Yeah, I didn't catch all of it. It was the idea to change the targeted searches instead of looking for a few minutes to look for a few years.
Instead of a few minutes, stare at a star or a star system for a few years.
Stare at the same star for a few years.
There might be a flicker once in a while or something.
Yeah. Well, I mean, it's certainly been advocated. You know, God, we're only spending a couple of minutes at any given frequency on any given star. That doesn't sound like much. Maybe we ought to spend longer. Well, maybe we ought to spend longer, particularly if they're pinging us, you know, that kind of thing. But here's the trade-off. If you're looking at individual stars one at a time, looking for these long-lived signals, is it a better strategy to spend that time staring at this one star, or is it a better strategy to say, look, that star had its chance of going to other stars? Right? Maybe only one. I mean, if you think Frank is right about 10,000 societies in the galaxy that are clever enough to want to get in touch with you, then roughly one in a few million stars will have such a society. So how long should you spend on any one of them? And this is, you know, you don't know the answer to this question until you've learned the answer to the question. In other words, until you found something. Then you'll know what the better strategy is. And until then, you just have to sort of go with what you think is most reasonable. And at this point, it's always considered better, go to another target. So, I have sympathy for your idea. Yes, ma'am.
Two items. One, a personal request. On your one slide where you referenced Marconi, could you please add the name Tesla? And the second question is, you said nobody reads Russian literature. What if they send messages to us in Russian? What I'm trying to say is, if your equipment's reading a math system with base 2 and they're sending a message in base 12, you know, how are you reading these things?
Okay, I got to cut you off there because that's 4 questions. but they're good ones, all right? And the first one was to mention Tesla. Okay, well, I'm a great fan of Tesla too, Nick. You know, and indeed, he was as important for radio, I'm sure, as Marconi, in fact, maybe more. But of course, you know, radio waves were predicted by Jim Maxwell, right, in the 1860s during the American Civil War. So you ought to give him credit. And then again, there was Heinrich Hertz, who actually generated radio waves in 1888. So, you know, it's a long history. It was a shortcut for which I apologize. The second question was, yes, nobody reads Russian papers. What if they're sending us messages in Russian? Let me point out something about that, actually. People usually assume that one of the things that SETI does is you get all these bits coming down the pipe out of your radio telescope, and you're analyzing them, looking for patterns. I think the value of pi is in here, George. I don't know, I learned that in 7th grade. It'd be kind of disappointing if they sent me the value of pi, but okay, maybe it's a Fibonacci series. I read Dan Brown. You know, we don't do that, because what we do is we integrate. We average the signal for a couple of minutes, the couple of minutes we're looking at any given frequency, in order to beat down the noise. It's like making a time exposure on Skyline Drive out here of the Silicon Valley at night. If you hold the shutter open for a minute, then you can see all this faint stuff, but the stoplights all look simultaneously red, yellow, and green because you've lost the temporal information, right? Well, we do the same. So we're losing all the bits. Right, all the modulation, that's all gone away. It's just a signal. All we know is they're on the air. And if you take, for example, a television signal, you average it for 3 minutes, you know, a lot of the entertainment value goes away. and I know my friends in the audience are thinking, there is no entertainment value. But okay, so, with that example, if you could just barely detect the signal in 3 minutes, then you would need 10,000 times more sensitivity to get time resolution of like a microsecond, so you can see the signal. So in other words, for the lay audience, here's the deal. You find that they're on the air, and now you have to build something much, much bigger to have a chance of getting the message, at least in the radio. In the optical, it's a little different, but in the radio, okay? And you know, you say, well, is that going to happen? I think it's going to happen. I mean, if the SETI Institute or one of the other SETI experiments around the world, there aren't many, by the way, you know, there's a small handful, were to announce, we got a signal coming from 750 light years, and it's at this frequency, and it's around that star there, I think that funding would cease to be a major problem. And I think you would have the money. You'd have a worldwide effort to build that very large antenna and then get all the bits, and everybody would download these bits onto their hard drives, and there would be plenty of people who spoke Russian in case that's what they're doing. So I don't worry about that. But I don't know that they'll be in Russian, Chinese, or anything like that. They're going to be, who knows what they're going to be. A lot of people say mathematics. I'm not that keen on the mathematics approach to language because it's hard to describe things like art and government, you know, with mathematics. But maybe they'll just send, said some guy today, just send a picture dictionary. A lot of pictures with a lot of words, and then after that send plain text. Or just send their version of the internet. It's so redundant that you'll figure some of it out. So I'm not too much worried about the language problem.
With the 350 arrays, isn't SETI afraid that the FCC will fine SETI for producing a signal for more than 50 hertz, causing earthquakes and lightning strikes?
You're going to have to repeat the essence of that. My hearing, I guess, is not very good because I didn't quite get it. We're worried about the FCC being concerned about the signal being broadcast by 350.
Producing a signal more than 50 hertz, which is the standard that they only allow a certain signal. I believe it's less than 50 hertz.
Okay. Can somebody who heard that tell me? Did you hear it? Are you worried about a signal at 50 hertz? Or?
I believe that the FCC has a set standard where they have the
Yeah, right. Are you worried about, okay, so you're worried about the health effects of powerful transmissions?
Yes, there is a satellite, or not satellite, excuse me. There is a system in Alaska that can produce 1 billion hertz.
Yeah, you know, you're worried about the HARP system and stuff like that. Now, look, to begin with, we're not broadcasting at all. Right? We don't have any transmitters on those antennas. I mean, Arecibo has a transmitter used for radar studies of the solar system and also the upper atmosphere. But we don't broadcast at all, so there's not much danger there, right? In fact, the only danger at the observatory are the bees and the snakes, but not from the antennas. So I don't see that as a problem for us. You might say, well, the aliens, you know, they're not going to allow very, very powerful transmitters because of the health effects, but you don't have to have the transmitter on your planet. I mean, I think if you had a transmitter, you know, running at 10 to the 17 watts, if you could do that, right, you would definitely have it in space. And 10 to the 17 watts, Barney Oliver used to say, you know, waveguides melt. He had a point there. And I don't think 10 to the 17 watts is very feasible. Yes? Yeah. What if they're not using radio waves? They're using some other communication mode that we don't know about. I have to tell you, it's a good question, and I get this question every day in email, usually 5, okay, along with the ones that are having difficulties with aliens in their personal lives. I get 5 of those too. And by the way, I don't think anybody's hoaxing me. They're all very sincere people. I kind of enjoy talking to them, but I don't know that any of them have proven to me that they're being really visited. But I'm getting off the subject here. What was the question? Yeah. No. What if they're not sending radio? Well, that could be. And the suggestions that I get are, you know, why not gravitational waves? And we haven't chosen radio simply because we can do radio. I mean, there is some element of that, right? Why are we doing more radio SETI, for example, than optical SETI? Well, I think that's mostly historical. Radio was invented really before lasers were invented. It took a while to figure out that the lasers actually offered you the opportunity because you can aim a laser into a mirror this big, right? And it makes a very tight beam on the sky. I mean, you know, optical photons are very expensive in terms of energy, but you can focus them very inexpensively, and consequently that makes sense. Had we invented the laser before we invented powerful microwave radio, maybe we would be doing more optical and less radio. But it's all the same thing. It's still all electromagnetic radiation. And we know that that travels at the speed of light, and it's relatively inexpensive to produce, and at least in the radio, goes right through all the stuff that hangs between the stars without impediment. So it really works as a communication medium. People suggest things like gravity waves. That's their favorite, gravity waves. Now, you know, we haven't even detected gravity waves yet, even though they're big instruments. It's very hard to detect gravity waves. And by the way, it's also very hard to make gravity waves of any size, right? You got to do things like take a star and shake it, right? Now, that's a big project. Even when left to the students, that's a big project. Whereas making a radio wave that you could find, 1,000 light years away requires building a transmitter that fits on this stage. Okay, so what I say to these other people is, well, what do you suggest? And, sometimes the suggestions sound intriguing. Neutrinos and so forth are often suggested. Hard to detect neutrinos, but they have advantages. The one big advantage of neutrinos, you don't really have to aim the receiver. Right? The neutrinos come right through the Earth, so even if they're down there, you can find them. Right? That kind of thing. But on the other hand, the detection efficiency for neutrinos is very, very low, and so forth and so on. They're very expensive. So, if you got a better idea, send me an email. But I have to warn you that a lot of people have done a lot of thinking about this.
What do you think about the latest reported evidence indicating possible bacterial life on Mars? In particular, they've ruled out meteorites as the source of the amount of methane they're detecting in the atmosphere, and also a reinterpretation of the Antarctic meteorite suggested that the small fossil-like structures were similar to magnetically sensitive bacteria on Earth.
Yeah. Well, I think many of you are familiar with the story of life on Mars having several lines of evidence suggesting life on Mars. Of course, the big science news story of 1996 in August was the Martian meteorite ALH 84001. And some NASA scientists at Huntsville and also Richard Zare here at Stanford University opened that thing up, and they claim that they have seen evidence inside that indicates that there were microbial Martians at least 4 billion years ago. Now, that's very contentious, and it has been ever since the announcement, and I think it's still contentious. A lot of it hangs on the interpretation of these magnetic materials in there, which look like the kind of magnetic materials that bacteria make on Earth. But I'm not the one to ask about that. Actually, at the SETI Institute, we have on the order of 60 scientists, 50, 60 scientists, and almost all of them are astrobiologists. SETI is a small part of that, okay? And the single subject that is most studied at our institute is Mars. So I recommend you get in touch with some of those guys and ask them their opinion. But at this point, I think they would all agree that while there are many suggestive things, like the methane on Mars is very suggestive, right? That it's not at the point where you say, we know there was life on Mars or that there is life on Mars. It's still indicative and not definitive. I think that that's fair to say. Yes, sir.
I read something a while back that was thought-provoking, and I'd like your thoughts on it. The possibility of detecting signals depends not only on how many intelligent civilizations exist, but on how long their technological capability persisted. And since the age of the universe is, roughly 11 billion years or something like that?
Yeah, 13 billion.
15, big number. If there's only 10,000 order of magnitude intelligent civilizations to look for, the probability that they all exist at the same time as us seems pretty remote. So how do you factor in the simultaneity of our technological capability to listen and the capability of someone else sending to be existing at the same time?
Yeah, the gentleman's question has to do with the fact that, why do you think that they're out there broadcasting now? The universe is very old, and maybe they, those radio waves that would indicate ETs out there have washed over this planet, 300 million years ago, and the bivalves didn't find them. Or maybe they're going to come in another 300 million years. But all of that is encompassed in the Drake equation, right? Because that last term in the Drake equation, L, how long a civilization lasts, actually deals with it. And this is the way to look at it. Suppose I ask you, how many students are at Foothill College, for example? Or at Stanford. Stanford, to make it easier because it's a 4-year school. How many students are enrolled at Stanford? Well, you could figure that out. You can make a pretty good estimate by saying, look, how many freshmen are admitted every year? Take that number and multiply it by the average number of years they stay there, which is 4, right? So that gives you the number of students at Stanford, fairly accurately. Well, what Drake was saying, and this is the right way to look at it, it seems, how many societies are born every year in the galaxy, right? Intelligent societies, societies that are technological. How many come online, if you will, every year? And that number might be less than 1, but it's some number. And then how long do they stay in that transmitting state? It's completely analogous to the Stanford example there. And that gives you the number that are broadcasting signals that are going right through your bodies as you suffer through this presentation. And that's the number that was estimated at being millions by Carl Sagan or 10,000 by Frank Drake. It's the number that are contemporaneous with us, that are out there now, if you will, broadcasting now. And they're time of flight issues here, but they're not important. Okay, got that? Let's take 2 more questions because I know looking stultified. Yes?
All right. Assuming that we do find an extraterrestrial intelligent life, and paranoia aside, what rational planning have we done to prepare for this mathematically probable?
Yeah. You're asking, what planning have we done to prepare the world for this news?
More like, what are we going to say to them?
What are we going to say to them? Oh, that's okay. That's a different thing.
You can answer the other one, too.
Yeah, I'm going to answer both. Okay. As far as preparing for how we deal with the news, there is, in fact, there's not a whole lot of preparation. I mean, I don't know that Spain did a whole lot of preparation for the eventuality that, Chris Columbus might trip across a new continent. But we've done more than that, and there is actually a document, it's called a protocol, which I think is a very unfortunate name. And in fact, a committee that I chair at the International Academy of Astronautics has recently revised that document. It's very simple. We've simplified it and removed some incongruities in it. All it does is say, look, if you find a signal, you verify it, and then you announce it to the world, right? The first thing you do is you tell all the astronomers in the world, because you want them all to train some instrument, whatever instrument they have, in the direction of this thing. And then, then you tell the press and the government. In fact, we've already seen that what happens is that the first people to know are the press, right? Because there's no secrecy in SETI. There's no policy of secrecy, right? A lot of people like to think that there is, but there's not. There really is not. As soon as we get a signal that looks interesting, everybody's emailing their, girlfriend, well, Madge, don't tell anybody, but we got this thing. Madge's brother puts it on his blog, 5 minutes later. I mean, in a sense, it's not such a good strategy, because that means there are going to be a lot of false alarms, and you could worry about credibility. But, in fact, there is no secrecy. So that's what it says. And then it says one more thing, and that is no response to a detected signal will be made without international consultation. Now, that originally arose during the time when the Soviet Union was still in existence and also doing SETI. And, there was some level of distrust that if the Soviets found the signal, they might monopolize it, not tell us, and broadcast back signals and, get them on their side kind of thing, It make a lot of sense to me. But anyhow, all right, or that we might do it from the Soviets' point of view. So in order to forestall this, we all agreed, look, if you find a signal, you tell everybody, and you don't start trying to get in touch without international consultation. And it was never specified what international consultation was, right? Did you tell the Swedish checkers team? Was that international consultation? Was it the UN? That kind of thing. Nobody knows. So, but on the other hand, it was kind of a guarantee that nobody would rush to the transmitters and start broadcasting their personal philosophies to the aliens. Now, there are people who think broadcasting anything would be dangerous. And in fact, there are people in the world who wanted us, as a SETI group, to forbid anybody to transmit even ab initio. In other words, without finding a signal, to transmit to, Betelgeuse or something, your favorite, a song you composed last weekend, because they might launch the rockets and you'll be responsible for the destruction of the world. There are very serious people who think this is an issue. I don't think it's an issue, not just because I'm sanguine that the aliens are not going to, launch their missiles against Earth. They're very far away. But beyond that, and are they really that aggressive? But of course, who knows? But the real point is this: if you're really worried about that, you better petition tomorrow to shut down the BBC, NBC, CBS, and all the radars down at the local airports. Because they are broadcasting, and they have been broadcasting for a long time. So that's what they'll get first. Okay. Anyhow, I hope that answers your question. In terms of what it means, of course, to get a signal, that depends on whether we can ever figure out what the information content is. If you can, statistically, they're way ahead of us. Okay? They're not at our level. That would be highly improbable. That's like taking a wheel of fortune with maybe 10,000 slots on it. Right? They could be 0 years ahead of us, 1 year, 2 year, all the way up to 10,000. For example, spin it once. What are the chances that they're fewer than 100 years ahead of us? 1%. Right? So they're going to be way ahead of us. So if you can understand it, it might be very interesting. It might be very interesting indeed. I don't count on that, but I think the real thing you learn is that what has happened on this planet has happened on many other places in the universe. Okay, I see that is it. I want to thank you very much. If you want to come see me, I'll be upstairs in the back. If you bought a book, I'll sign it. Thank you.
Great. So thank you all for coming. We hope to see you at future lectures. Thank you, Seth, for a wonderful evening, and he will be available to sign books right at the top of the auditorium. Thank you all. Good evening, everyone. My name is Andrew Fracknoy. I'm the astronomy instructor here at Foothill College in Silicon Valley, and it's a great pleasure for me to welcome everyone in the auditorium and everyone listening or viewing us on the web to this lecture in the 11th annual Silicon Valley Astronomy Lecture Series. This is a series sponsored by the Foothill College Astronomy Program, by the NASA Ames Research Center, one of the premier NASA centers around the country, by the Venerable Astronomical Society of the Pacific, which is devoted to sharing astronomy with the public since 1889, and by, appropriately tonight, the SETI Institute, the Search for Extraterrestrial Intelligence Institute, which is devoted to the science and education of the search for life in the universe. This is a series of 6 programs every year where noted astronomers share with us the exciting results of what's happening in our quest to understand the universe. Tonight's speaker is Dr. Seth Shostak, one of my personal favorite speakers in the world of astronomy, who's going to talk about the search for intelligent life among the stars, new strategies. Dr. Shostak is senior astronomer at the SETI Institute and a spokesman not just for the Institute itself, but for astronomy in general. You often hear him on local and national radio and television programs. He also hosts his own syndicated radio show called Are We Alone?, which is broadcast locally here in the Bay Area on KALW and KLIV, and can be heard on the web. If you go to the SETI Institute website, you can find that program. And every week he has exciting guests talking about interesting developments in science and science's relationship with other fields. Dr. Shostak has written hundreds of articles and web pages on the quest for life elsewhere and other topics in astronomy and astrobiology. He has a degree in physics from Princeton University and a doctorate in astronomy from Caltech. For the last 6 years, he's been a distinguished speaker for the American Institute of Aeronautics and Astronautics. He's written and edited a number of books on the search for life elsewhere, and his most recent book is designed for the public at large. It's called Confessions of an Alien Hunter, a scientist's search for extraterrestrial intelligence. It was published by National Geographic Books, and I highly commend it to everyone who's listening to this lecture. So we've asked him to talk about one of his favorite subjects, the search for cosmic company. It's a distinct pleasure and a privilege to introduce Dr. Seth Shostak.
Thank you very much, Andy, for such a nice introduction. I'm afraid that the packaging will be better than the meat, but it's very nice. And I also, by the way, always warn audiences not to applaud beforehand because you will always have regret later. It's nice to be back at Foothill College. Actually, when I first came to this part of California more than 20 years ago now, I had a lot of free time, which is not the case now, but I had quite a bit of free time in the evenings, and I came up here and took some courses in creative writing, actually. It was somewhat by accident. I just wandered into the wrong room by mistake. And I have the fondest memories. I think that Foothill College, to the extent that I can write, taught me how to write. So it's very nice to be back here and to be back part of the lecture series. It's been a while since I've given a talk here. My last talk was what happens if we find ET, and in that I described a little bit about how SETI, and in particular the SETI Institute, which, by the way,